Okay, so this is going to be an overview on how VR works and how you use this to find your final slicing. So, as I briefly mentioned in the previous video, VR is a two-step method. I guess I should have called this two-phase method when I was thinking about this, but it's too late now. Two-phase as in like the Cosamba two-phase algorithm. It's a two-phase algorithm in order to find the best slicing. So, yeah, step one, which is to reduce to fiat group. So, well, if this worked, that would be great. To either solve, in which case you win 2x, 2x, 2e, 2e, or 2e, 2e, 2x, 2x. Anything works, okay? One of those 8 states that I showed you in the previous video. And then step 2. Insert E2s. So, we'll just briefly talk about the complexity of these two steps. Step 2 has linear complexity. It is really fast. And like even by human standards, this is really fast because you can just sweep once through the skeleton, and I'm just gonna tell you, you're gonna have to look for 2 edges throughout the entirety of the skeleton, basically. I mean, yeah, and by 2 edges I mean 2 locations, so you don't have to track anything. Okay, just look at the spots and see stuff. So yeah, so checking any single VR is going to be very easy. This is one of the things that makes this method so good. Because if you had to do an extra search in step 2, this wouldn't be more feasible than just doing one single search. Step 1 technically has exponential complexity. However, for one thing, the base of the exponential is 2 rather than 4. So that's one thing. Although I guess you can choose to widen or not. But also, it's just easier because so it's exponential, but not the total number of U moves, but just the number of quarter turns. So yeah, and because you're not gonna have more than 5 quarter turns most of the time, it's gonna be very rare to have more than 5 or 6 VRs you can find. There are also tricks for finding how many VRs you have. And by tricks, I mean like a formula, really. It's not complicated at all. Although like it's a formula that kind of depends on the condition, so you're gonna have to check that if you want to use it. But I mean, it's step 1 is easy enough. The real trouble is really checking all the VRs. You don't just find one VR and then solve it and call it a day. That's not gonna yield the optimal solution most of the time. You're gonna have to check multiple VRs, and this is really where most of the brute force comes in. So I'm just gonna be doing like a made-up example. So we have a leaf slice skeleton, and we want to find the optimal slicing. So before like going to my made-up example, I'm going to be imposing 2 conditions on this leaf slice skeleton. So the first condition is that centers are either solved or each away from being solved. Basically, I don't want it to be in E or E prime, but E2 is fine, and it's not even just like you have to rework your method and you can such that it works with E2. It's just not even a difficulty you have to overcome. Like there's nothing complicated about having them E2 away. And the second condition is that there's no simultaneous U or D moves. No, UD moves. And this is to make sure that you cannot insert a slice and add negative number of moves. So just as an example, if you have UD2, you can insert E2 here, and this will become UDY2, which is U prime Y2, which is fewer moves than we started. Like you have UD2 and now you have 1, and because rotation is not a move. Fun fact. So this is what we don't want. And the good news is that most of the time you can rearrange your skeleton. You can just insert slicing your skeleton so that you avoid this UD2 thingy. Now, technically, there is one case where you cannot avoid that, and that is when you reach DR, and you have to do UD to get to HDR. That's the only exception. You cannot get rid of that single UD. But this is very, very, very rare. So I'm not even going to consider this. And also, I feel like you should work out what to do in that case, if you ever get that. I certainly never got in that case. I don't think anyone ever got that case. So let's just go ahead and line made up example. So I'm just going to make some imaginary buckets, I guess, where I'm going to have the VRs in plus 0. We're not finding them yet, and just like we know they exist. Well, I guess technically, like this is a set, so it exists even if it's empty. VRs in plus 2, VRs in plus 3. And okay, obviously this bucket should be bigger, but yeah. So okay, let's just find the VRs in plus 0 now. Okay, let's say we found 4 VRs in plus 0. And now we need to check them. So let's say, for example, the first yields a plus 2. Okay, great. The first VR yields a plus 2, so this means that we can just throw out everything here. Why? Because from a VR in plus 2, we cannot hope to get anything better in plus 2. The length of the VR is a lower bound to the length of the final solution you can get from there. So having already found a plus 2 means that we don't need to check, well, definitely don't need to check for VRs in plus 3, but in VRs in plus 2, because we already have plus 2. And so we will be doing extra work just to find something that like a move count that we already have. And so we only want to be doing extra work if you have the possibility of finding something that's strictly better than what we already have. So this is why we throw away the VRs in plus 2. And let's just say we're unlucky. We get plus 3, another plus 2. That's useless. And here we get real unlucky, we get plus 4. Generally not what's going to happen. What's going to happen generally is you're going to have a plus 1 somewhere. If you get a plus 1, actually it's very nice because you can just end the search like the VRs in plus 0. You don't even need to check for the next VRs. So that's extra nice. But let's just say you get something really, really unlucky like this. This is not common at all, because especially when you have this many VRs. Okay, so now let's just find the VRs in plus 1, and generally it's going to be more. Okay, let's just say here we have. Oh, here I'm unlucky, we found a plus 2. Here we find, well, a plus 1, but it's no use for us plus 1, because you already have a plus 2, and this is at best a plus 1. But say, here we got a plus 0. Okay, we stop. Why? Because we found a plus 1. And anything here that cannot be better than plus 1, because the VR is plus 1 already. So we can just throw out the rest, and we're done. So, yeah, basically, a way to think about this is that the solutions that we find are an upper bound to the cost of the final slicing, and the length of the VRs that we're checking is a lower bound to the cost of the final slicing. And so you only want to be checking VRs with length strictly less than the best thing you found so far. And as soon as you find as soon as you find something you can prune off some length, some VR costs, and as soon as you find a plus 0, you can just stop the search immediately. Okay. If you hadn't found a plus 0, then I mean, we would be exhausting all the VRs in plus 1, and then it would be done because we already like eliminated this. To end the video, I'm just gonna be writing some pseudocode just to finalize the algorithm that you should take. The pseudocode really follows from what we just said, but hopefully this. I mean, for some of you, this might be a better explanation. I don't know. So, it's going to be bad pseudocode. It's just going to be, but whatever. So I'm just going to be initializing a couple of variables. Best so far. Starts with PE. And I'm going to initialize this to 8, just because 8 is the worst move count of a slice state. Really, you're never going to have 8 in isolation if you have a non-trivial skeleton, because having a single move just guarantees, well, actually I think it guarantees plus 6. So, maybe plus 7 is possible if you have a U. I don't know. Yeah, I think it is, but just initialize to something really big. And then let's initialize n to 0. And we're going to be running a while loop. So while n is less than best of r. Now we're going to be generating a list of all the VRs in plus n. So find VRs in plus n. Just inventing the name of the function, I guess. So now for VR in L, we're gonna let current move count, I guess current cost I should say, check VR. And so now what we're gonna do is we're just gonna update the best so far variable. Actually, one thing, if current cost equals 0, return. And this is kind of what I mean, but I'm writing this badly because like we should be returning the final solution or like the length or whatever. I'm just gonna write return because like I'm lazy. You can do this for an exercise if you want. Exercise with the viewer. And now we're just gonna update the best so far as being the minimum between best so far and current cost. And at the end, we're just gonna have n plus equals 1 lined up with this. And I guess we kind of return something at the end. I don't know. There is one little caveat with this, is that this only looks for slicings. It is technically possible that you just have to just insert a full 2e, 2e, 3e, 3e, 4x algorithm to solve the slice optimally, and you can't actually even you do slices. But that's very rare. It requires a very short skeleton. But I guess if you worry about this, technically you should be adding at the end a routine to just look for algorithms insertions. I think it's guaranteed that you only have to insert an algorithm once. You don't have to do multiple insertions, because otherwise you should be able to find this using VRs, or like it's gonna be worse than just inserting one algorithm anyway. So yeah, so I think that's it for the overview. I am gonna be making an example at some point, so if you didn't understand how this search works, yeah, just look at the examples to see how it works, basically. And in the next video, I'm just going to be showing how to do step 1. So stay tuned for that. Or I guess don't. I think I'm planning to release all of these at once.